So in this lecture I will discuss the Sobolev spaces W1G and W012G. So once for all G, it's an open, bounded subset of Rn. G is fixed once for all, and I will represent by C infinity 0 of G. This is the set of functions U from G to R, which are C infinity, which means that they have all derivatives and in every directions, and the support of U, which is a compact set, it's contained in G. So let me take two functions, U and V, in C infinity 0G. And you can integrate it by parts to get the following relation, that the integral on G of the derivative of U in the J direction times V dx, that this is equal to minus the integral of G of U dx J V dx. So this holds for all test functions U and V and for all G between 1 and D. And mind that there is no boundary terms because I'm assuming here that the support of U is contained in G, and therefore that the boundary values of U and V at the boundary of G is equal to 0. And this formula, so we want to extend the derivative to a larger class of functions. And the definition I'm giving, it's based on this identity. So assume that there exist two functions, U and W, in L2 of G, such that the following hold, such that for all test function f in C infinity 0 of G, we have that dxjf times U dx, and this integral is over G, that this is equal to minus W f dx on G. So suppose that there exist two functions U and W in L2 such that for all test function f in C infinity 0 you have this identity. If this happens, then I will say that U has a generalized derivative in the jth direction, which is given by W. And I will represent W by dxj U. So if this identity holds for all test functions f, I will say that U has a generalized derivative in the jth direction, which is given by W, and I will represent W from now on by dxj U. Now, first observation is that, well, dxj of U, it's uniquely defined. So assume that you have two functions, W1 and W2, such that U dxjf dx, it's at the same time equal to W1 f dx with a minus sign, and also W2 f dx. What I claim is that if this holds, then W1 and W2 are equal in L2 of G. And here, of course, I'm assuming that these are elements of L2, right? And you see that all these integrals are well defined because I'm assuming U and W1, W2 to be in L2. On the other hand, since this holds for all function f in C infinity 0g's. Since I'm assuming that f belongs to this space, f also belongs to L2, and therefore this scalar product, these integrals, are well defined. So what I'm claiming here is that this partial derivative of u, this generalized partial derivative, it's well defined. Because if you assume that there exist two functions, w1 and w2, for which this identity holds for all test functions f, then I claim that w1 is equal to w2 in L2. And this is clear because it follows from this identity that w1 minus w2 f dx on g it's equal to 0 for all f in C infinity 0 g. And since this space is dense in L2, of G, I can find a sequence Fn in this space which converges to W1 minus W2 in L2. And from this identity, if I take that sequence and I let n to infinity, what I get is that W1 minus W2 square dx is equal to 0, which means that W1 is equal to W2 in L2G. So my first observation is that, well, this derivative is well defined. Now let me give you an example. So I'll take a one-dimensional example, G to be equal to minus 1, 1, and U of x to be equal to the absolute value of x. So here is the interval minus 1, 1, and here's the function. And what I claim is that there exists a generalized derivative, and the generalized derivative dx of u will be equal to minus 1 for x between minus 1 and 0, 1 for x between 0 and 1, and at 0 I can define dxu to be equal to c, where c is any constant in R. So what I have to prove in order to show that indeed u has a generalized derivative given by this formula is that for all function f in C infinity 0 minus 1, 1, we have that dxf in minus 1, 1 u dx. So let me call this function w, that this is equal to the integral from minus 1, 1 minus f w dx. So let's prove that indeed we have this identity for all functions f in C infinity 0 minus 1, 1. So let me write the left-hand side of this identity as the integral from minus 1 to 0 of dx. So let me write that as f prime. And then u, but u in this interval, it's given by minus x. And then in the interval 0, 1, we have still f prime of x. In the interval 0, 1, absolute value of x is equal to x. So the left-hand side can be written this way. Now let us integrate it by part. So you see f, I assumed f to have compact support in minus 1, 1, which means that at minus 1 f is equal to 0, while at 0 x is equal to 0. So there will be no boundary terms when we integrated by parts this expression. So this is equal, by integration by parts, to minus 1, 0 f dx. And now let's do the same thing here. Again, f, it's assumed to have compact support in minus 1, 1. So it vanishes at 1, x vanishes at 0, So there is no boundary term when we integrate this expression by parts, and we get that this is equal to the integral from 0 to 1 of fx dx. So I can rewrite this expression as minus the integral from minus 1 of fx wx dx. The value of w at a point does not matter because it's a set of measure 0, which will not change the value of this integral. And on the other hand, well, w by definition it's equal to minus 1 in the interval minus 1, 0. So indeed, between minus 1, 0, we have minus with minus plus. And w is equal to 1 in the interval 0, 1. And indeed, we have here minus, and here we also have a minus. So we proved that indeed this identity holds for all test functions f, and therefore that u, which is the absolute value of x, has a generalized derivative which is given by this function. So this example shows that we have functions which are not differentiable, but which have a generalized derivative, and here as the absolute value of x. And now I can introduce the space W1 to G. So this is the space of all functions u in L2 of G. So remember that G is an open-bounded subset of Rn. These are all functions u in L2, such that for all G between 1 and D and N, there exists Wj in L2 of G, such that for all f test function in C infinity 0 of G, we have that dxj f u dx in G, it's equal to minus wj f dx. So W1 to G is the space of all functions u in L2 which have generalized derivative in all directions as we defined before. So this is the definition of our space. And now, so here n, let me just remark that I'm assuming that G it's a subset of Rn. So this n represents the dimension in which we are working. And I want to define a scalar product. So now if I have two functions, u and v, in W1 to G, I want to define the scalar product of u and v, and this will be the scalar product in W1 to G, which I will represent by 1, 2. Well, this will be the usual scalar product in L2 of u and v, plus the sum from 1 to n of the scalar product of the generalized derivatives. So these two scalar products are scalar products, the usual scalar products in L2. Here we are taking the scalar product with u and v, and here the scalar product of the generalized derivative in the jth direction of u and the jth generalized derivative in the jth direction of v. I will show that this is indeed scalar product, but let me just introduce a notation to simplify. So I will represent by gradient of u. So this is a vector whose coordinates are given by the generalized derivatives. So with this definition, so now gradient of u, I'll call that the gradient, the generalized gradient of u. With this notation, I can rewrite this scalar product in a simpler way, saying that this is just the gradient of u times the gradient of v, and this is representing now the integral, if you wish, the integral over g of the gradient of u times the gradient of v dx. And, well, let me show now that this is indeed a scalar product. So my claim is that 1, 2 is a scalar product. And for that, we need to prove all the properties. So let's prove them here. The first property is that this scalar product is linear, and this is clear. Remember that I'm always working here on the field of real numbers. So the scalar product is linear, and this follows from this formula. On the other hand, if I assume that, so this is the first condition. The second condition is assume that the scalar product 1, 2, it's equal to 0, then, well, this implies that the usual scalar product of u, the L2, so here 1, 2 refers to the scalar product 1, 2, and when I don't write anything, I'm just taking the scalar product in the usual L2 space. Since each term here, if v is equal to u, it's positive. If this scalar product is equal to 0, this means that each term is equal to 0, and from that you conclude that the first one is equal to 0, which means that u is equal to 0. And the third property, which is required by a scalar product, is that it is symmetric, but this is clear from the definition because the scalar product in L2 over the field of the real numbers, it's also symmetric. So indeed, this is a scalar product. So now let me prove the following proposition, that W12 endowed with a scalar product 1, 2 is a Hilbert space. So we have to show that it's complete. So to prove that it's complete, let me take a sequence un, which is Cauchy. Cauchy for the norm 1, 2. Remember that u1 square is equal to the norm of u square plus the sum from 1 up to n of uj square, of the partial derivatives of u square. And this means that if un is Cauchy for the norm 1, 2, this means that un is Cauchy for the norm L2, and dxj un is Cauchy for the norm L2. So we know that un is Cauchy for L2g, and dxj un is Cauchy in L2j. Well, since L2j is a Hilbert space, this means that un converge to some u in L2j. And since L2j is complete, this means that this object converges to a function which I will call vj in L2. Now, what I want to claim is that my claim is that u has a generalized derivative in the j direction, which is given by vj. So to prove this claim, let me take a test function f in C infinity 0g, and let me use the fact that un has generalized derivative given by the derivative of un in the j direction. So this means that the integral of dx j f un dx is equal to minus the integral of j dx j un dx. Now let's recall that un is converging in L2 to u, and that dx j un is converging in L2 to vj. And since they are converging in L2, they are converging weakly, so I can take the limit on both sides. The left-hand side converge to, so the left-hand side of this identity converge to dxj f u dx, and the right-hand side converge to minus f vj dx, because dxj un is converged to vj. So since each of these terms is equal, the limits are equal, and we get this identity for all test functions f, which means that u indeed has a generalized derivative given by vj. So this means that vj is equal to dxj u. So let me erase the claim which I just proved to complete the proof of the proposition. Now I proved that un is converging in L2 to u, and that dxj un is converging to dxj u in L2 of g. So you see from this formula that un minus u in the norm 1, 2 square, which is given by this expression, that this is converging to 0 as n goes to infinity, which proves that indeed the Cauchy sequence un converge to u in that 1, 2g, which proves that 1, 2g is a Hilbert space. So now let me define the Sobolev space W0, 1, 2 of G. This Sobolev space is, well, you take the space of test functions, which is, of course, a subspace of W1, 2G, and you complete it in, so you close it in W with respect to the norm W1J. So W0, 1, 2 of G is the closure of C infinity 0 G, the closure for the norm of W1, 2 of G. So this is the definition of the space W0, 1, 2. And the claim is that W0, 1, 2, G is a Hilbert space. And this is clear because, well, if you take a set Y, so we already proved that if you take Y, a linear subspace of a Hilbert space X, then the closure of Y is a Hilbert space. And this is exactly what's happening here. We have the space of test function is a linear subspace of W12G. So its closure, it's a Hilbert space, and this is exactly the definition of W012. And what I want to convince you now is that this space, W012 of G, is in some sense the subspace of functions in W1 to G which vanish at the boundary. So this is not a precise statement, but I will give you some examples. I will prove some properties which indicate that indeed this is the space, so W0 it's indeed the space of functions in W1 which vanish at the boundary. So my first lemma is in dimension 1, or n equal to 1. So say that you have a function u which belongs to W0, 1, 2, an interval ab. So let me fix minus infinity smaller than a smaller than b smaller than plus infinity. So a bounded open set in R. And what I claim is that if you have a function u which belongs to this space, then there exists a continuous function v in CAB such that u is equal to v almost surely, and v vanish at the boundary. So any function in W012, of course this function v, it's uniquely determinate, because if you have two continuous functions which are almost surely equal, they are equal at every point. And what this is saying is that, well, this continuous function vanish at the boundary. So in some sense, u, it's vanishing at the boundary because it's, if you take a representative which is continuous, there exists one, this one vanish at the boundary. So let me prove this lemma. And, well, this lemma, it's giving a meaning to this informal statement I introduced, saying that indeed we can think of this space as the space of functions in W12 which vanish at the boundary. So let me give a proof of that. So let me fix x in the interval AB, and let me consider a function u, which is, or f, which is continuous. So fx let's assume that this function f vanish at the boundary, or maybe let's assume that this function is a test function c0 infinity. So since this function vanish at the boundary, I can subtract, so I can write fx as fx minus a. I can write this as the integral from a to x f prime z dz. So now if I take the absolute value and maybe the square of that, what I get is that this is equal, and now I can use Swartz inequality to bound this expression by x minus a times the integral from a to x of f prime z square dz. And of course this is bounded by b minus a times the integral from a to b of f prime z square dz. And this is bounded by b minus a times the L2 norm of f prime square, but this is also bounded by the norm 1, 2 of f square. So what I proved is that fx square is bounded by this quantity for all x, and therefore you see that the right-hand side does not depend on x, so I can take the supremum over x in AB. And what appeared, what I just proved, is that the infinity norm of f, it's bounded by square root of b minus a, which is the length of g times the norm f1, 2 of f. So what we just proved is that the L infinity norm of a function f, test function, so I wrote, I took AB, closed AB, but what I really wanted is the open interval AB. The argument is exactly the same. And so we just proved that for these test functions, the L infinity norm of f, it's bounded by a constant times the 1, 2 norm of f. Now let's fix a function u with in W0, 1, 2 of AB. So by definition, we know that there exists a sequence Fn in C infinity 0 AB, which converge in W1, 2 of AB to U. So let's consider this sequence Fn which converge to U in W1, 2. And let's observe, let's apply this inequality to Fn minus Fm. So Fn and Fm are functions. This space is a linear space, so the difference also belongs to this space. Therefore, I can apply this inequality, and this inequality tells me that this quantity, it's bounded by Fn minus Fm 1, 2. But now, since Fn is converging to U in W1, 2, this sequence is Cauchy in the norm 1, 2. Since we have this bound, and here is the infinity norm of Fn minus Fm, we get that Fn, this sequence of continuous functions, it's Cauchy in C AB. Now, since it's Cauchy for the sup norm in the space of continuous functions, we get that Fn converge to some function f in CB for the infinity norm. And now you see that on the one hand, Fn converge in W1, 2 to U, and on the other hand, it converges to f for the infinity norm. So what I claim is that this implies that f it's equal to U almost surely. Indeed, we have seen that convergence in W1, 2 implies convergence in L2. AB, I don't write AB anymore, and also convergence in L infinity implies convergence in L2. So we have the same sequence which at the same time is converging in L2 to U and in L2 to F. This means that F it's equal to U in L2 AB, and therefore they are equal almost surely. So we proved that indeed there is a function v which is continuous. This is our function f here in the proof, such that u is equal to v almost surely. They are equal in L2. And moreover, since Fn is converging to f in the L infinity norm, Fn are functions in C infinity 0 AB. This means that these functions vanish at A and B. And since the convergence is taking in L infinity, this means that f of A is equal to 0 and f of B is equal to 0, which is the second condition. So this completes the proof of the lemma. So let me insist here that in dimension 1, this lemma is telling us that the functions in W0, 1, 2 have, in some sense, a boundary value equal to 0, in the sense that there exists a continuous function which is equal to u almost surely and whose boundary values are 0. So this is confirming our general statement that W012 represent functions in W12 which vanish at the boundary. So let me give you a second argument to say that W012 corresponds to the functions in W12 which vanish at the boundary is the following theorem, which I won't prove. So if you have a G and you assume that its boundary is smooth or locally smooth, then I claim that you can prove the following, is that for all functions u in W1, 2 of G, that the integral over the boundary of G of ux sigma dx, so here it's you're taking the measure on the surface at the boundary of G. I claim that this is bounded by a constant which depends on G but not on u of the norm of W of u, 1, 2 square. So I want to prove this inequality for a very special set G. So I assume that G it's a rectangle and in dimension Rn. So I'll prove it in dimension 2, but you see that the proof I'm giving works in any dimension. And for the proof, let me call that A1, B1, so, and A2, B2. So G will be A1, B1 times A2, B2. And I will prove that, well, for C1 functions, so I'll assume that U belongs to C1 of G, which means that U has continuous derivatives in all directions on this set, and these derivatives are continuous up to the boundary of G. And I'll prove this identity, this inequality for these functions, and to extend this inequality for such functions to the functions W1, 2, we need an argument which tells us that this space is dense in this set. So let me prove this result, and then we will consider later the problem of the density of this space. So let me fix a function u in C1 J, so the closure of G. And let's consider the left-hand side. So the left-hand side, well, we have the boundary, so I can divide the boundary in 4 pieces. I will consider just one of these pieces. The other ones can be estimated in exactly the same way. So I'm here interested in, say, that boundary in which the first variable is fixed to be equal to A1, while the second one run from A2 to B2. So I have an integral from A2 to B2 of u. So the first one is fixed to be A1 y square dx. And I want to estimate this quantity in terms of the norm 1, 2 of u. So what I will do, I will use essentially Swartz inequality. So let me write that as a2 b2 dx. And here I will subtract and add 1 over. So here I'm fixing a point. I'm sorry, this is y, of course. So I'm fixing a point here, which is a1y, and I want to compare this value with the average of u on this line. So this average is given by b1 minus a1, the integral from a1 b1. Here the value y, it's fixed, and I'm averaging over the first coordinate. So I'm adding and subtracting this quantity, and once I add and subtract, I will use the inequality that a plus b square, it's less or equal than 2 times a square plus 2 times b square. So I first subtract and add, then I use this inequality to say that this is bounded by 2 times plus 2 times the integral from a2 b2 dy, and I have here b1 minus a1, the integral from a1 b1 u x y dx square. So let me continue. So let me erase the statement, and let me continue with these 2 terms. So I have here 2 terms. I will bound each one separately. So let's consider the second one, which is easier. So for the second one, I will just apply Swartz inequality here inside to say that the second term, it's bounded by, I already have a 2. Then I have an integral from a to b2 dy. And now I can use Swartz inequality to bound this expression by b1 minus a1 times a1 to b1 u x y square dx. And now you see that what appeared here, so that this is equal to 2 times b1 minus a1, and here I have exactly the L2 norm of u square. And this is, of course, bounded by 2 times b1 minus a1, the 1,2 norm of u square. So this is how we estimate the second term. And let's remember this estimate, and now let's estimate the first term. So let's turn to the first term. For the first term, since I have an average here, I will insert this quantity inside the average. And I will rewrite the first term as 2 times the integral from a2 to b2 dy. Now we have b1 minus a1, the integral from a1 to b1, u a1 minus u a1y minus u x y dx. And there is a square. Okay, so, well, since I have the square, I can consider here I have uxy minus ua1y. So I have this term here minus this one, and I will write this difference as the integral of the derivative. So this is an integral from a1 to x, the derivative in the first direction, so dx of u of z y dz. So this is this difference, and this difference is integrated from a1 to b1 dx. So now I can write this quantity as 2 times, let me take b1 minus a1 square outside of this integral, and let me use Swartz inequality. So maybe before we use Swartz inequality, let me bound this expression putting an absolute value in this term. So once I place an absolute value, I have an inequality, and once I have this inequality, I can replace x by b1, because this is positive, and x it's between a1 and b1, so this is smaller if I integrate everything up to b1. And once I do that, I notice that this expression does not depend on x anymore. So this integral, this is a constant in x, so this will give me a b1 minus a1 factor, which will cancel to this one. So I can just erase this integral and cancel this denominator. So this becomes 2 times, and I don't have anymore this integral. So up to now, I proved that this is bounded by, I hope you followed the computation, a1 to b1, the absolute value of dxu at zy dz square. Right? And once we have that, now let me use Swartz inequality to get this square inside at the cost of a factor b1 minus a1. And now you see that what appeared here, it's exactly the L2 norm square of the dxu. So this is equal So at the end, we proved that this is bounded by b1 minus a1, the norm of dxu in L2 square. And this is, of course, bounded by 2 times b1 minus a1 times u 1, 2 square. So in conclusion, what we proved is that this integral, it's bounded. So the integral of u on this boundary, it's bounded by a constant which depends only on a1, a2, b1 and b2, so on g, say, times the norm of u 1, 2 square. And we can repeat that on the other boundaries to get a general result, which is the one which I stated and which I'll state it again. So what we proved is that if I integrated on the boundary u x square dx, that this is bounded by a constant which depends only on g times u 1, 2 square, and we proved that for all functions u in C1 G bar. So this completes the proof of this inequality. So we just proved the following proposition. I took as set G the space, well, it's open, A1 B1 times AN BN, this hyperrectangle, and we proved that there exists a finite constant which depends only on G, such that for all u in C1 G bar, which means that it's once differentiable, its derivative is continuous up to the boundary, then it holds that the L2 norm at the boundary of u, so if you integrate it at the boundary, the square of u, that this is bounded by this constant times the HW12 norm of u. So two observations. The first one is that if you're able to prove that C1G is dense in W1, 2, you can extend this inequality to all functions W1, 2 just by density, by taking, by approximating a function U by a sequence UN in C1. And the second remark is that, well, actually you don't need G to be that regular. You can prove this proposition if G has a smooth boundary, but I won't do that in these lectures. And the last observation is that now assume that U belongs to W0, 1, 2 of G. If W belongs, this means that you can find a sequence UN in C infinity 0 of G such that UN converge to U in W1, 2. So consider this sequence. Well, what you have is that the integral of UN minus U square by the previous inequality, that this is bounded by the constant G times UN minus U 1, 2 square. Well, on the one hand, well, UN is converging to U, so this expression is converging, this difference is converging to 0. On the other hand, UN belongs to C infinity 0, it's a test function, which means that at the boundary it's equal to 0. So what we have is that actually this integral, it's equal to U squared dx. And therefore, since this is converging to 0, what you can conclude by passing to the limit is that the integral of U squared dx it's equal to 0, which means that if U belongs to W0, 1, 2 of G, then, well, the average of U, of the square of U at the boundary of G, it's equal to 0, which means that at almost every point of the boundary of G, U it's equal to 0. And remember that I wrote here dx, but what I really mean is that you're taking the measure on the surface, so this is a surface measure, and which can be written as sigma dx, and here I'm writing dx just for simplicity. But it follows therefore from this proposition that if U belongs to W0, 1, 2, its integral, the integral of its square at the surface of G, it's equal to 0, which means that U is equal to 0 at almost every point of the boundary.